Welcome back to the afternoon session. They were lucky to have Samory Kpotufe from Columbia to give us talk about transfer learning. Samory's been working on non-parametric statistics, active learning, dimensionality reduction, and today he'll tell us about his latest work on transfer learning.
Thank you. Hi, everybody. So thank you for being here in this afternoon session. I'm tired. I'm sure a lot of people are tired. But let's try to go through this. I'll be talking about transfer learning, as the title says. And by transfer learning, what do I mean? I mean transfer learning, domain adaptation, all these names that just talk about distribution shift. Right. I never know exactly what is the definition of transfer learning because there are so many names that appear all the time. But mainly, I will mostly be talking about is the following. Prediction. I have data from some distribution P and a little bit of data from a distribution Q, and I want to do well under the distribution Q. That's the high-level problem. And what I'll talk about is the essential, the key element of this problem, which is how to measure the relatedness or discrepancy between P and Q, right? Between these two distributions. What is the notion of information that P has on Q so that so much data from P might help us do well on Q? So that's the key question. And this talk is going to be based on joint work with various collaborators over the years. And much of what I'll focus on is mostly work with Steve Haneke. All right, so please interrupt me anytime. I try to prepare not too long of a talk so that you can interrupt me anytime. And so most of the work is going to be on trying to really understand what we mean by relatedness. And how do we capture it and what we want out of a good measure of relatedness, okay? I'll start off by just motivating the whole problem, motivating the type of questions that we'll like to be able to answer, and start trying to give some answers to these questions. It will be statistical questions and it will be algorithmic questions, okay? So, here is a basic motivation. I start off with mostly IID data. I'm in the setting where there is IID data from a distribution P, and IID data, labeled IID data from the distribution Q. So that's the simplest setting, and that's the setting we're going to consider. I'll mostly talk about classification, even though transfer learning is about classification, regression, and all sort of other problems, but the focus will be on classification. Some of the things I'll talk about will touch on regression, and towards the end, I'll try to give you some new insights for a paper we just put on arXiv yesterday, that appeared on arXiv yesterday, about how to really unify all these ideas, okay? Again, IID data from the distribution P. Here, I'm not even talking about having data from the distribution Q, just to sort of set up the problem. And here's the case study. I keep using this case study, Apple Series voice assistant, because I've been quite annoyed with it. It just cannot understand my accent for some reason, till now, actually. And the way I see it is that it was initially trained on American English accent, and I view that as the distribution P, the source distribution. And yet it was to do well on every English accent. And I view that as the target distribution, okay? And what is the solution? Apple, it's doing much better now. And what Apple had to do was acquire a lot more data over time, and retool these algorithms to start doing better on the general population. And so the problem in transfer learning is how to reduce this cost, how to quickly do well on the target distribution using extracting the most information possible from the source distribution. I hope that's clear to everybody. So it's of general relevance, and hence a lot of papers on this subject recently. AI for judicial systems, source population tend to be people already in the prison system. Target population is everyone arrested. you have these type of issues happening in medicine, genomics, and all that, because target data, which are viewed as the ideal data, is hard to acquire. And so we tend to use source data that is somewhat related, and hence the question of what do we mean by related, right? All right, so I'll now give some basic questions that sort of will drive the rest of the talk. So basic questions that a practitioner may ask. So I have, suppose H hat is some classifier trained on source data from P, and it is to be transferred, and by transferred, I mean it is to do well under risk, under the Q risk, under the risk under a different distribution, okay? So a first question is there sufficient information in the source about the target, and what do we mean by information, right? A second question, if there is not sufficient information, how much more data should we acquire in order to retool? Would unlabeled data help? The reason why we ask this question, practitioners ask this question, would unlabeled data help, is that unlabeled data is cheaper to acquire, right? This is another question that we started off on years ago. It became too difficult and we didn't go too deep into it, but I still like to put up this question. So suppose that I'm Google and there is a particular cost for acquiring data from P and a particular financial cost for acquiring data from Q. Is there a notion of optimal cost if I want to achieve a particular error? And then is there an algorithm that can achieve this optimal cost of data acquisition in more of an interactive data acquisition scenario? So that's the high-level question. But you can see that all these questions are related, and a lot of them have to do with understanding what do we mean by information about that P has on Q. In statistical terms, I just say, what is the relative statistical value of having data from P versus having data from Q? And how far is P from Q? I'll use the term distance, I'll use the term relatedness, all that to mean the same thing. I hope that's clear. All right, so how do we proceed? First, as it turns out, a lot of the work on transfer learning, I mean by that the theoretical work on transfer learning, a lot of the theoretical work on transfer learning has focused on the case where you mostly have data from the source distribution, but no data from the target distribution. So a first thing, actually, I'm getting ahead of myself. I just wanted to talk quickly, just say something I'm not going to talk about much. There is tons of work in the non-parametric setting on transfer learning. However, we don't have time to get into this part, the various works in the non-parametric setting. We'll mostly just focus on the case of fixed VC dimension for classification. If we're in regression, the parametric setting, maybe linear regression and such things. So that's all we're going to try to talk about. So as opposed to much of the work that mostly look at the case where you have source data, but no target data, we're going to consider settings where we have both source and target data. But that recovers the setting where we don't have any target data, because I'm allowing NQ to be anything and P to be anything. Fine. And this is important. Why? Because let's go back to the original question. I want to understand the statistical value of data from P versus data from Q, and I want to understand, therefore, the limits of transfer learning under both sample sizes. If I have a learner that has access to two samples, what is the best possible risk of that learner in terms of both NP and NQ? And here, I'm interested in excess risk under the target, the QSS risk. Fine. So the statistical question is that, what are the limits? Please.
You know both P and Q?
I don't know the distributions, but I have data from both of them.
Okay.
I just know it's data from two distributions that are potentially unrelated, that are potentially not the same. So the statistical question is, what are the limits? And by limit, I mean minimax type rates for given classes. What are the limits of learning in this scenario? Which notion of distance, by distance here, I just mean quote unquote, relatedness, which notion of distance between P and Q captures this limit. Both the data from P and Q. H-hat is any algorithm allowed to have access to both data sets. And then the algorithmic question is this. Once we've understood the statistical limit, or once we're starting to understand the statistical limit, often these type of limits are given in an oracle sense. The oracle has access to some distributional information. I'll be clear as to which distributional information the oracle has access to. Then I ask the algorithmic question, is there an actual algorithm that can adapt to this limit? For instance, without knowing this distance, is there an algorithm that can achieve the best possible rate in terms of whatever notion of distance there is? Fine. And so that's the adaptivity question. And both questions are quite important, these two. Any question about the setup? All right. So similar questions in
Does the algorithm get to know that there are distinct samples from P and Q?
The algorithm knows that this is the sample from P, this is the sample from Q. The other case is much more complicated. I don't know what can be done. I think Daniel has worked on the other case, no? No, he's worked on everything. So, all right. So we can ask these questions for various other problems. I hope that's clear. Okay, so the outline is the following. I'll start giving you a little bit of background about various relatedness measures that people have looked at in the literature, and also discuss what might be missing from these various measures, the ways people have tried to capture this question. And then I'll get into a first proposal, and that's a proposal that a proposed measure that Steve Haneke and we've worked on, and that has also a non-parametric counterpart. I'll talk a little bit about it. Then, after that, I'll tell you why I don't like that measure that we propose, and because it doesn't give a unified understanding of the problem. And then I'll talk for about 10 minutes about a more unified understanding, a more unified notion that we just put on archive, that I just appeared on archive yesterday, that tries to recover a lot of the past work on the subject. Right. Then I'll get into negative results for 5 minutes, about 10 minutes. And these negative results are really just a way of just trashing my own work at the end and telling you everything that actually sucks about it. Everything that's not good about it. So I hope that's clear, what we're doing. So we'll start with related measures and what's missing. And so in about 10 minutes, I'll try to tell you really about 10 to 15 years of research. And so I apologize to people who have worked on all this, because I'm just going to give a general sense of what these works have been. All right. So classification, many competing notions have been proposed, and so I'll focus on classification. Many proposed notions are there. And I'll use this simple cartoon. So in this cartoon, what do we have? We have some source distribution made up of this object, and some target distribution that tends to have a lot more of the triangles on this side. So there is a shift in the distribution. So there is really two general lines of work on notions of distance. The first I will just call extensions of total variation, right? So total variations and extensions thereof, and which essentially measure the distance between the two distributions as the difference in measure over subset of the space. The refinements that have been proposed by people like Shai Ben-David, Miriam Mori, and co-authors over the years have been to focus on these regions of space that are defined by the hypothesis class, by differences, by where the hypotheses disagree. Okay, because that's the most relevant part of the space. So that's mostly just a quick summary of this type of work. And the type of excess risk bound they obtain are of this form, this additive form. So essentially, part of the rate goes to 0, and then plus this additive term, distance between P and Q. And the main thing that actually, one of the things that brought us to this work is really this additive term, and which essentially is saying that even in situations such as I described here, there is no consistency. You essentially asymptote to the distance between P and Q. And I'll argue that there are tons of situations where this should not be the case. I hope that's clear.
The first term goes to zero, you want like
In NP, yeah. So here I'm just giving that type of work where they're only considering source distribution. The whatever learner they come up with. No. That's the question she just asked. So here I'm just assuming no Q data. So there are terms that are left which I'm not putting, but the fact is that there are these additive terms. The most important is this one. Okay. All right. So then there are density ratios, things that have to do with divergences and such. And often this comes from, this is due to algorithmic reasons. If I could estimate this density ratio, I should be able to estimate the risk under Q from just data from P by importance sampling, right? And so we can then view the type of rates that are obtained by these procedures as, again, something that goes to zero plus the estimation error. And this tends to sort of suggest that transfer learning is as expensive as density ratio estimation, which is a hard problem on its own. So again, we'll argue that it's probably, in a lot of situations, it's probably not that expensive, right? It's like solving a harder problem to address sometimes a simpler problem. All right. So in fact, many notions have been considered. Any notion of distance between distributions, any metric, any divergence, anything that was proposed out there to measure the distance or the similarity or dissimilarity between distributions has been attempted in transfer learning, in the theory of transfer learning. And the type of results they obtain tend to be of that same form, that if P and Q are close to each other under the choice of metric, then transfer learning is easy. Then we can transfer from P to Q, right? So that's sort of the gist of a lot of these results. And the question we are asking is a bit different. We're asking this question: do these notions really capture transfer learning, in the sense that if P and Q are far from each other, does that mean that transfer is hard, right? Is that sort of clear? And so we'll argue that there are tons of situations, and I'll just go through little pictures, that there are tons of these situations where, in fact, P may appear far from Q under these various notions, but transfer is actually an easy problem.
We're not distinguishing between closeness or hardness of the joint distribution of XY and the conditional distribution.
Okay, for the sake of this presentation, I'm just, for these examples, I'm just looking at distance in the marginal X. However, we can go beyond that, right?
In your previous slide, just to kind of get bearings for what the problem is like if we just look at the density ratio case, is the problem that it's the wrong metric on the density ratio? So for example, I only care if I'm estimating the density ratio inaccurately near the decision boundary.
You're getting actually very close to that.
So it's not that the density ratio is flawed, it's just the way that we're looking at it.
It's sort of the way we're looking at it, but in fact, we don't even need to care about density ratios, and I'll get to it in a minute, because there will be situations, tons of situations where, in fact, density ratio is ill-defined. However, we can transfer well, right? So that's not even but it's closer. It's about the decision boundary. Is that sort of clear? So quickly, one situation is this. Suppose this is the support of P. Suppose this is the support of Q. The support is this line, and the support is this line. I'm in linear regression. Linear classification. I have plus, I have minus. Right. There is no density ratio, doesn't say anything here yet. learning on the P allows me to learn on the Q. Right. If this is the best classifier for both of them.
Is the issue one that came up, I think, in some other talks, which is you really only care about the optimal.
It's exactly. Yeah.
Not the whole class.
Not the whole class. That's actually very close to the issue. Exactly. And so that's the main hint, is that I'm going to mostly care about the decision boundary, not about the whole class. And so let me get into those examples now. All right. So let's look at this quick example. Suppose we have this source and this target. We can imagine already it's clear that on the total variation, I can make these two distributions far from each other. On the DAY discrepancy, these extensions of total variation for linear classifiers, I can also make them far from each other. But immediately you can see that if I learn a linear classifier here, it will do well here. Right. And it's not just about linear classification. If I did a nearest neighbor using this data, it should do pretty well here. So it has more to do about how much the source is revealing this decision boundary than anything else, right? Here, I want to argue that metrics in general are not the right way to capture whatever notion we want to capture, because metrics impose symmetry, and transfer is an asymmetric problem, in the sense that I may have a lot of information on the decision boundary relevant to the target from this source, but not the other way around. Fine. So whatever notion we're looking for should be something asymmetric, not penalizing me for having being matched with a bad other distribution. Right.
In this case, it seems we should just have a conditional rather than a marginal.
Sorry?
In this case, for example, since the conditional distribution of the two classes is the same.
Yeah, so these examples here are really just to get some intuition about the problem. Right now, yes, in these examples, the conditional distributions are not necessarily the same, but the best predictors match each other. Right. So that's the main thing here. And then eventually, this is just to give some intuition. Eventually, we'll remove needing even the best predictors to be the same or matching each other.
I think someone asked you this, but throughout I should think of the only thing that's changing is the marginal distribution.
I'm saying for now. For now, it's for these simple examples, it's easiest to think of it that way. Okay, but we'll just look at the general case. I hope that's clear for everybody. So the main point I'm making here is that metrics probably are not the right thing. So we have MMD, Wasserstein distance, and such things that people have tried, but they are all metrics and impose symmetry in the way they measure the relation between the two distributions. All right, so then what about asymmetric notions such as KL and such? So here they are based on density ratios also. They are based essentially on the well-behavedness of these density ratios. And so here I'm looking at the target, and the target, I'm assuming that the target is lower dimensional than the source, so that these things are not well-defined. So similar to this example in some sense, so that these things are not well-defined. Yet, again, if I learn a linear classifier here, it does very well here. And if I use this for nearest neighbors, trees or such, it will do well on this problem. And everybody's sort of, a lot of people have touched on the main intuition already, that it's more about whether or not the source is revealing something about good predictors under the target, right? And so we'll try to capture that intuition, and that will be the next proposal. Is that clear to everyone?
So what do you want to transfer? Do you want only very good algorithms to transfer, or do you want every algorithm to transfer?
Okay, so the basic problem for me is just this. I want to do as well as possible on the target, and that's it. And I have all this data from some other distribution. So
you're assuming we can kind of like optimize for P that is not computationally
So yeah, so I'm just assuming, yeah. So some of the algorithms I'll talk about might not even be computable, but the key question on the statistical part, especially, I'm trying to understand: is there an algorithm at all? The existence of an algorithm that can optimally, in some sense, to be defined, optimally use the source data combined with the target data and do well on the target data. So I guess I hope that answers.
So for all of these kind of like distance-based things that we're summarizing, when you say like a distance, sorry, it goes back to the marginal question. It's like you assume some kind of upper bound on some distance for the marginals and some Lipschitzness on the predictors or something, like that's sort of the flavor.
Right now, so far, I haven't proposed anything. I haven't assumed anything.
But like the form of the result, I guess, like the distance will be on the marginals, and then you will.
I'll give the form of the result in a second. Okay. All right. So these are just little examples to motivate what I'm about to do. All right. So a first attempt, and so now I'll give some concrete stuff, and relating source P to target Q. So this is something that we we proposed some time ago to try to capture this intuition that it's really about how well I'm doing, how well the source is revealing something about good predictors under the target, right? So a basic way to restate that is that if H has low error under the source, it likely has low error under the target. So that's a first attempt, a simple first attempt. And for now, I'm going to assume that H star P is equal to H star Q, that there is an H star, there is a best classifier under the source and a best classifier under the target, and they are the same, right? So that's a first basic assumption. I'll remove that assumption. This is, again, to give intuition, okay? Then the first proposal is this so-called transfer exponent. It is just a way to capture, to parameterize this intuition. It just says that driving down excess risk under the source drives down the excess risk under the target, and it says at what rate, right? And that's all it is. It's just a simple parametric form to allow us to start answering some of these questions that I posed in the beginning. It is completely arbitrary, but it is a first way to try and capture this intuition. I hope that's clear to everyone. Okay. Why polynomial form? Because polynomials are nice to work with, right? All right. So this simple thing will be shown to capture some type of continuum between easy and hard transfer, and especially going back to one of the questions I asked, which was if P appears far from Q, does that mean that transfer is hard? And some of those notions I was showing that, okay, P and Q can actually be very far under, let's say, total variation, nearly 1/2, which will say that transfer using those bounds, which will suggest that transfer is not possible, yet transfer is possible at fast rates. And this simple notion already starts getting rid of that when rho is small, transfer is easy. When rho is large, at the very least, there exist distributions for which transfer is provably hard. I hope that's clear.
So, I mean, to some extent, just assuming a transfer exponent seems to just, solve the question of, it just by fiat assumes something transfers.
Mm-hmm.
Is there a sense in which, maybe for linear classification, something about the distribution of examples, you can then bound the transfer exponent? So are there data generative models or assumptions where you can...
I'll give some examples to give some intuition about the transfer exponent. And then when I get to the other part where I'm talking about a unified measure, your question will be better answered, because in that case, we actually can rebound things in terms of existing measures. Is that clear? Yeah. All right. So this is really just to gain more intuition about the problem and about the sources of difficulty in transfer learning. So we parameterize things this way just to gain intuition about the sources of difficulty in the problem. So I'm going to assume something further. This is not an assumption in the papers. It's just an assumption for this talk, just to understand things, that y is given by h star of x, okay? And so that I can view the excess risk as just the measure of the disagreement region. All right, so here, suppose that I have these two distributions. These are their densities, uniform, but on different parts of the space. And I look at this. Let's say this is H star. I look at the disagreement region between H star and H star T, H star and HT. Then we can see quickly that the rho is just essentially 1 because the constant absorbs the different in that ratio of the mass of these two regions. Right. Clear to everyone? So this will be an easy problem. This is just to give a sense of what the easy problems are. This will be an easy problem, rho is 1. Here is another case where rho again is 1, but you can see this is the case where KL and all those divergences don't make sense. The other situation is one where I can in fact, because of this region, force extensions of total variations to 1/2 essentially, okay? And yet transfer is easy. It's just measuring really how much mass, and that's the way to view it. It's measuring how much mass the source is giving to the decision boundary. Okay. Again here, similar thing, measuring approximately how much mass, how much is the source revealing the decision boundary that is relevant to the target. Okay. Fine. All right. So here for general rho, this is what happens. Again, I'm letting this be uniform. Now I'm letting P, the source, decrease really fast around the decision boundary. So it gives very little mass to the decision boundary. And then you can show that in situations like this, rho just has to do with how fast the source decreases around the decision boundary. Okay, and so intuitively, this will be a hard transfer case. The source is not revealing much about the decision boundary compared to the target. If I flip it, so now the target has little mass around the decision boundary, the source has a lot of mass around the decision boundary. This is a situation I call super transfer. So it could be that in fact, the source is better for me than the target data itself, right? And in this case, rho is below 1. That's a good question. I forgot to say that. For simplicity, I just say for all H. But in fact, when you look at the definition, you'll see that the definition is witnessed only by H's that have small source error. So it's localized by itself.
Right, because if you went back to your pictures where the supported Q was a subset of P, right, then for some H's, this would not hold.
Yeah, no, I'm just saying that this definition is immediately localized, right? Because I'm looking at classification loss, which is bounded, and so I can just not care about the things that have large error. Okay.
But this is also goes back to the question I asked earlier, which is that this kind of transfer works for every good algorithm for P. You don't have to assume that you're
about you don't have to so I was talking to Siva some time ago about it, and one way to describe this type of work is unstructured transfer. I'm not assuming anything much more than these two distributions are different, and what can I do if I don't have any other information, right? And how can I measure things?
So since you're looking at the excessiveness, so on the left-hand side now, should I think about if I had as much data from Q as P is the excessiveness, how should I think about because I can, I'm just trying to understand in what notion are we trying to say how good should it do on Q?
I'm not following the question. So this is really just saying immediately, if I did well on P, how much have I driven down the risk on, I did well on P, yeah, how much did I drive down the risk on Q, right? It is just a read-off. No, it's not symmetric. It's a completely unasymmetric notion. That's what I just showed in this flip, right? Make sense? Yeah. Okay. All right. So let's make things more rigorous and say what is rho revealing about some of the questions I asked earlier. What are the limits and which algorithms achieve these limits? Are there adaptive procedures and such questions? So before I can talk about the performance limit, this is classification. It turns out that it's not only the distance between P and Q that affects how well I can do in transfer learning, it's also about how easy the problem is. And so here is a quick explanation, and most people here know what we mean by easy classification problems. It has to do with margin, it has to do with the noise and such. And so that's all I'm drawing here. This is an easy classification problem. This is a hard classification problem. One way to capture it is through a so-called Bernstein class condition. Peter has worked a lot on these type of conditions. And you don't have to remember this formula. Just recall that this beta is going to appear, and the beta has to do with the amount of noise essentially around the decision boundary. Okay. Clear to everyone? And the beta would tell us between whether we're going between whether we have fast rates or slow 1 over square root n type rates, and that's all it serves. But it turns out that the beta is quite important for the algorithmic question. When is it that we can adapt to the minimax rate? Okay, and which was surprising at first, but intuitively it makes sense. Low noise, under low noise conditions, the problem is easy, adaptation becomes easier. So for the sake of this talk, I'm just only going to assume a single noise condition on both source and target. In the paper, there is a beta P, a beta Q. Okay, those who are used to Tibakov's type of noise conditions, if H star is the base, then you can relate the two. All right, so given we are given here labeled source and labeled target, and the minimax rate is what I'm giving in terms of this row here. The minimax rate takes this interesting form. There is some, essentially, I call it the effective sample size contributed by the source, plus the sample size contributed by, plus the sample size from the target, to the 1 over 2 minus beta. Again, if beta is 0, we get the usual 1 over square root n type rate. If beta is 1, that's a low noise condition, we get fast 1 over n type rate. Fine? To everyone. Tightness. Here I emphasize that the rate is tight in the following sense. It's tight for any VC class H, for any value of rho greater than 1. For the values of rho less than 1, we just showed that there exists a class H for which this is tight, and for any value of the parameter. So this is a tight rate. Why am I emphasizing this? Because often people just say this is tight without characterizing in what regimes is it tight. Okay. Clear? I hope everybody's used to minimaxity. I'm just saying here that there exists an algorithm that knows that can achieve this rate. And for any algorithm, there are distributions satisfying these conditions that for which it cannot achieve this rate. Okay.
So for the settings where you have like rho less than 1,
Mm-hmm.
and let's say beta was 0, so somehow even when NQ is 0, you can get like a better rate. Is that what was the super
Transfer? Yeah. Okay.
So for these types of theorems, is the algorithm always just ERM, or is there
So that's leading to
weighted thing?
no, yeah, that's exactly leading to the question of the algorithmic part. So right now I'm just giving you the oracle rates, and I'll in a second discuss algorithms. Okay. Here, a quick answer to your question is this. Here is something. If I assume that NQ is 0, then the rate is trivial, right? Because you can just read it off of the definition that the accessories on the Q is NP 1 over rho, right? The question becomes interesting when I have 2 sample sizes, and then I ask which algorithm can achieve this rate under these 2 sample sizes. Is that sort of clear? Then I'll talk about it in a minute, which algorithms can achieve this. And in those cases, it's not just ERM, but it's penalized versions of ERM, and I'll give a sense of that in a second.
I guess it would almost seem like, just taking the theorem, literally, that I would kind of want that really the blow up in sample size tells me the way to weight the two importances.
Yeah, but the question is, I don't know rho. Is there a way I can do this, right?
The question is, can you remind me what rho is?
It is that that transfer exponent. It is just a way to relate how fast I'm decreasing target error given a particular source excess risk.
When you say NQ is 0, the problem becomes trivial. Does that mean rho and beta will be related if NQ is 0?
No. I just mean if you read it off of here, if NQ is 0, the rate I'm getting is just NP minus 1 over rho to this power, right? That's all I'm getting. And I'm saying that by the definition of what rho is, it's trivial. That's all I'm saying.
Okay.
All right, so quickly, benefits of unlabeled data. How am I doing on time? 25 minutes, 30 minutes? Yeah. Okay, benefits of unlabeled data. So that was a question. Is unlabeled data useful here, right, to this problem? Can I add on unlabeled data to this IID data I have from P and from Q to drive these rates down? So in the worst case, no. That's the answer. In the worst case, no, because the minimax rates, the lower bound, is established under the assumption that the learner has access to the complete marginal. And so it cannot be beat. And it turns out that I was talking to Shai, and he has some earlier, all the way down in 2010, some earlier results showing that unlabeled data, in the worst case, does not help transfer. More interesting for me was this, the benefits of labeled data, whether I can read off at what point, that was that question of, at what point is it that target data, I should, okay, that was the question of how much more target data should I acquire? And so by writing the rates in terms of both sample sizes, I can see at what threshold the target data is the one driving down the rate, right? And the threshold is essentially whenever I have this greater than this. This I won't talk about. It is a line of work that if anyone is interested, I can talk about, we can talk about it later. So this is where you have actual cost of sampling the data. Right. All right. So VC dimension is in here. I'm just hiding it. Okay. So it's like, and wherever you see NP, put NP over VC. Fine.
So based on this rate, is that fair to say we either do ERN on MP or we do ERN on?
Great question. Yeah. Great question. If we know rho, exactly. Yeah. So the question is this. This is a very beautiful way of writing this thing. It turns out that it is nothing else but the order of the minimum of this rate and the minimum of this rate. The minimum of what you could have done on the source and what you could have done on the target. That's all it is. But it's again, it's the minimum, not the maximum. It is as though the algorithm knows which of the source of the target is most informative towards doing well on the target. I hope that's clear to everyone. However, suppose I try to just, and that's answering your question a little bit, suppose I try to just use cross-validation to do this, right? Suppose I learn an ERM on the source, an ERM on the target, and I try to do cross-validation. What would I do cross-validation on? Probably the target data, but I only have an NQ of the target data. And my cross-validation error becomes an additive error on the rate I can guarantee. So I can only guarantee then a rate in terms of NQ, not the minimum of the two. I hope that's clear. Right. Now, another point I want to make there about the minimum of the two, that's the best you could do. Why? Because suppose, for instance, that P and Q were exactly the same distribution. Then what is the best I could do? I could do about 1 over NP plus NQ square root of that. That's of the same order as 1 over the max of the two sample sizes. So in effect, this is just to make us feel good that we write it as a sum of two samples. Yeah. Yeah.
And getting extra power from the P distribution. This seems really intriguing.
Yeah.
It suggests you might be able to design a
P? Or
That's actually one question that I asked myself a few years ago, and just I never had time to really think it through. That suggests that there is possibilities of designing a P that reveals the target more. But now, again, we do not know actually the decision boundary under the target. So how does one go about that? I have no idea. But but there are results where people design, in fact, distributions and seem to do well, better with their design distribution. So there are empirical results of that form that I've seen. Does that explain it? I have no idea, but yeah. Okay. All right. Okay, so let me quickly talk about the lower bound analysis. The main thing that is different in establishing these lower bounds is the fact that a lot of the tools we know in lower bound analysis, a lot of the tools we know sort of assume, not inherently though, but they sort of assume, or at least the way we apply it, that the data I have access to is IID, right? That I have access to IID data, and we use these information theoretic tools to say that, okay, this is given only this amount of samples, this is at most how well I can do, right? And here we have data from two different distributions, and so we just had to be a bit more careful about how to use that using the usual machinery. So the key difference for those who are interested in lower bounds, I like lower bounds only because it reveals where the source of hardness of problems are, right? So you construct a family of pairs of distributions, P and Q. The key difference is this, is that we force the pairs of distribution, the H here that indexes them, you can view the H as the best classifier for that pair. You compare any two pairs, they are close in KL divergence. So the construction is such that any two pairs is close in KL divergence, which makes them hard to distinguish from data. And yet, under only Q distance, they are far. So that's the key difference from usual lower bound, right? Is that in the usual lower bound, we make them close under KL divergence, measure under the same distribution, far also in the loss you want. And so here, we just had to combine distribution in such a way that the pairs are close, but under the marginal, they are far. And so that's the key thing. All right, so upper bound, that's where it gets interesting, and that start answering the type of questions, is we are interested in adaptivity. We don't know rho, can we achieve a result in terms of rho? And how do we achieve it? So this is where beta becomes interesting. Under low classification noise, it turns out that just combining source and target data and pretending they are from the same distribution, so that's naive classifier, achieves these rates automatically. Right. Then, if beta is not 1, you can show that this is no longer good. Actually, you can show that it has strictly worse rates. And then there is this other type of algorithm, which is some type of penalized risk minimization that achieves this rate. So what is this algorithm? Here, I'm still assuming that H stars are the same. I'll give you a different algorithm when H stars are not the same. That H stars are the same, so what do? I optimize source, but I retain all the good classifiers under the source. And then I retrain under the target. Yes, okay. Clear to everyone? How much do I retain? This is just, you can view it as terms depending on Rademacher, local Rademacher complexities. So you can view it as a measure of the variance of the error. And so this is essentially a confidence set. And then I fine tune on that confidence set, and that achieves this type of rate. Is that clear? All right, so quick summary, and then I'll talk for 10 minutes about. So here is the first proposal, captures a more optimistic view of when transfer is possible. So it can be very small even when other distances are very large. It starts revealing a sense of optimal heuristics. And here is a different heuristic that I give. In the paper itself, we give tons of different heuristics and analyze them. minimize. Now here I switch minimize source subject to a ball on the target if you have some target data. This is safer. And why? Because if it turns out that this term, the excess risk of the best classifier under the source is large, then this is safer. I first constrain on doing well on the target, and I can automatically detect situations like this and ignore the source data and use the target data instead. I hope that's clear. Right. So when H stars are different, this is the additive term. You get into it. And then part of what we try to understand is it avoidable? It turns out it's not avoidable. Then later on, it turns out that under some nice situations, it can still be avoided, but I don't have time to talk about that.
So I think about the penalized form of this problem. Like instead of minimizing RP of H subject to R cube H not very large, I can minimize RP of H plus, parameter times R cube H, right?
Mm-hmm.
Then it starts to look like a naive kind of a unique weighted problem where I'm just like applying a global weight.
Yeah.
to all the
So I'll discuss that in a minute. So for classification risk, we thought about that. Does that make any sense to some extent? If we are in regression, it makes a lot of sense because, okay, I have essentially a penalized risk minimization. Everything is nice and convex. L2 risk, for instance, I can take the Lagrangian. It turns out to be exactly what you're saying. And so that leads to simpler algorithms, but I won't have time to discuss that but we can talk about that. So weighing is an interesting question. At the end, I'll talk about weighing. If I have 5 minutes, I'll talk a little bit more about weighing a bunch of sources. What can we guarantee? Okay.
Yeah, quick question about the
Previous slide.
yeah, so does this give you a classifier that optimally works on P as well? So whatever this procedure is,
So this procedure is only focusing on working well on Q.
but does it just
So, but because you return only out of a ball for P, that ball is essentially retaining good classifiers under P, so yes. Is that, yeah.
but is it optimal under P or just okay until like
Oh, as long as whatever you're adding here is of optimal order. Right, yeah. Okay. Oh, I was just saying this, that suppose that I think about the guarantees that cross-validation will give me. The only thing I'm comparing, the only thing I know cross-validation is up to the variance in that sample size that I have, NQ, right? That variance order is about 1 over square root NQ, and that necessarily gives me, if I pick the best under that necessarily gives me that additional 1 over square root NQ. So I'll get a bound like this plus 1 over square root NQ. And the hard part, the big part of that is 1 over square root NQ, if NQ is much smaller. If this doesn't, does that make sense? Yeah.
Just to be fair about the rate, I mean, the constant is the first.
Of course, of course, of course. And in fact, we were playing with the real data, and a lot of times, simple cross-validation does better than this. And it bugged me. But I cannot actually prove much about it. Right. So that's a very good question.
First, about cross-validation. I remember there's some work saying that under your assumption of this margin type assumption, the cross-validation actually adapts to the beta. It's much better than 1 or square root NQ.
Yeah, no, fine. But even if I'm saying let beta be 1, even if you want, right? And let's adapt to the beta. I'm just saying if this was much better, you will not get it.
Okay. Yeah. Then
Yeah.
what about you change first on the pure source data, the other on pure target data, and then you compare them on your code out target data. If they have significant difference, then you use the target name. And otherwise,
Yeah. So what you're getting at is Lepsky. It's essentially this. What you're getting at is that.
it's a manual version of the cross-validation.
Yeah. That would work. That's Lepsky, right?
That only requires comparison between two.
Yeah. But that's essentially sort of what this is doing. Okay. All right. So let me move further because I think I only have about 10 minutes, 15 minutes left. 20 minutes? Oh, great. So, question? Sorry? Here?
That's the next line.
Mhm.
So, about that delta term, I try to understand it. Like, both H and H prime seem to make some sense. Can you comment on that?
Both H and H prime, sorry.
In the delta term by H prime, it also seems to make sense. Why is the H term on the right? Basically the question.
Oh, no. This is just the ERM. I'm just saying. This is just the ERM. I'm retaining every H that is not so far from the ERM. It's just notation, that's all. Right. Okay. All right. So there is that. And now I would like to talk about a more unified notion. So this is a new paper on archive. I hope it's not too much information and I can still give this piece of information. So the motivation is actually interesting. We have in domain adaptation, in the literature on domain adaptation, we have so many notions of distance, right? And yet here I come proposing yet another, and everybody's like, who cares? There are too many notions. And so one question is there a unified way of looking at things, right? And it turns out that the transfer exponent hinted at it, and at that point, we didn't know why we decided to make it something of that exact form. It was just arbitrary. And so here we just decided, okay, let's start looking at exactly what we were trying to say, which was this. So the way I'll try to measure the relation between P and Q is through a modulus of continuity between the two risks, right? So I'm just going to look at this entire function rather than giving you a distance. So rather than giving you a number, I'm just going to look at the entire function. And what is the function? It just says how, if I'm decreasing risk under P, it's saying exactly what I said before. If I'm decreasing risk under P, how much have I decreased risk under Q? So essentially, if I look at a small ball under P, how large of a ball under Q am I in? I hope that's clear.
When you say decreasing risk, do you mean as you vary H?
No, I just mean as epsilon goes down. I'm looking at entire balls in the hypothesis class. Right. As epsilon goes down, what is that function? That tells me how fast epsilon q is going down. I don't know what that function is, but I can just say the same algorithmic question. Can I just adapt directly to that function without trying to parameterize it, without trying to bound it and things like that? That's the question we're asking in this paper. Is that clear? Then the first question was, so I'm just repeating here as epsilon q goes down. And then the first question was, does this simple thing capture the past literature? How well does it capture other notions of discrepancy or relatedness that people have proposed in the literature? It turns out that it captures a lot of them fairly tightly because these notions serve to bound this modulus of continuity. I hope that's clear. So A of y divergence, yield bound of this form, epsilon plus the discrepancy measure plus some function of the H stars, okay? What's also nice for us here is that all of a sudden we don't need to care that we are in classification. This is well defined for any well-behaved loss. Is that clear? And by well-behaved, I just mean that the loss is finite for every H, okay? So then transfer exponent is immediately bounded. We go to regression. Other proposals in regression, linear regression, some simple proposals have been the ratio between covariances. In regression, it's immediately bound this modulus. Then Wasserstein distance for Lipschitz classes, it's immediately also bound this modulus. And Then the question is, what is the best rate we can achieve in terms of this modulus, and especially by an adaptive procedure? And so if we achieve a particular risk in terms of this modulus, we recover result in terms of other losses, in terms of other notions of distance, right? And the analysis here is going to be very generic. We just have a loss, and we just have a class, and we have this measure.
So, when you say you can bound this modulus using these other things, why does it not bother you that there are other terms?
Oh, that's actually the best. We just went and double checked, and these are the best bounds that people are actually getting. So the question I was asking is that next one. If I get a rate in terms of this, do I recover those bounds? Right. So was this sort of the essential quantity that we aimed at bounding? Right. All right, so theorem, quickly, there exists an adaptive H hat that achieves a risk of this form. Mean of epsilon q, delta of epsilon p, where delta is this modulus of continuity. Now, what is epsilon q? And what is epsilon p? I'll explain it in a second. But view it as depending on the sample size from q and depending on the sample size from p. Okay? So the adaptivity here just is through a reduction to the existence of what we call weak confidence set. As long as there is this weak confidence set in your particular problem, you can combine them to get a rate of this form that is immediately adaptive to this modulus without knowing what it is and without caring about any notion of distance that upper bounds this notion. Is that clear, what I'm getting at? And what is a weak confidence set? It's essentially this, right? It is a set that depends on data that for sure contains the best, the risk minimizers, the population risk minimizers under my distribution, and a neighborhood of it. And is contained in a ball that is not too large. Now, the radius of this ball is epsilon q and is epsilon p. That's all it is, okay? All right, so examples in classification, we can get rates of this form in terms of beta q, beta p. These were the noise conditions. In linear regression, we get rates of this form where it's a dimension in here. Again, VC dimension, I ignore here.
So, just so I understand, so the miracle is still the adaptivity. The first rate is ERM on Q. And
Exactly. Yeah. It's adaptivity in a two-sample setting. And then there is immediately also the question of, okay, I'll get to that question in a second.
So, and just building on that,
Yeah.
just to, I guess, reinforce and make sure I understand what you said.
Yeah.
A priori, the other bounds which you're recovering as a special case,
Yeah.
they might have had algorithms that might be tailored to the particular measure they have for the
Yeah.
difference of the distances.
Uh-huh.
But here, this is not using anything because it's just the modulus.
Yeah, it's just this modulus in the, and then we're just asking, is there, can you build a confidence set satisfying these particular properties?
So then my follow-up question
Yeah.
is, so here I know that you're sort of ignoring the algorithmic complexity of finding the H hat.
Yeah.
Could this actually change the algorithmic complexity? I mean, there could be cases.
So far, so we just put this on archive and we have a disclaimer.
Yeah.
There is very little in terms of actual good algorithms here. It's more about understanding, is this problem doable at all, at least in principle, right? And then it turns out that if the loss I'm dealing with is a tractable loss, and that these confidence sets are in fact tractable, then I have a tractable algorithm, right? And so for instance, in linear regression with square loss, these are easily built.
Right.
Okay.
So you're using the same loss function for both P and Q, right?
Yeah.
So is there any possibility that the loss function affects the upper bound of the delta?
Oh, the loss function definitely is determining what the delta is. The H, the hypothesis class you're considering, is determining, and the distributions are determining. Right. Okay, good. So here is some instantiations. And then there is the question of tightness. And the question of tightness is really on, how much time do I have? 9, thank you. The question of tightness is really an interesting question here. Why? But for a nuanced reason that I wasn't sure I was going to get into. Let's look back at this notion. Okay, actually, we can see it here. The notion is really just considering how well I do on the P without really considering the target data. Could the target data have helped me do even better than how well I would have done on the P without any target data? Because it's a nuanced thing. Because this is really just defined in terms of an epsilon that says I've done this well on the P. How well am I doing on the Q? Now I have a bit of data from the target. Is the mean between this and this the best I could do? And so it turns out that yes, in a lot of situations, it is the best I could do if I have source sample and target sample. Here is a quick situation where it's not. And 5 minutes about? Yeah. So here is a quick situation where it's not. So in this situation, I'm just going to consider having multiple best classifiers under the source. Okay. So I have multiple best classifiers under the source. And soon as I have a bit of data from the target, it reveals that this is not a good classifier. I should use this instead. Okay. So we can refine the modulus a bit further. This is H star P, H star Q. The original modulus was just telling me about the size of this ball. Right. Now, if I have a bit of data that says that on the Q, under the target, that says that in fact I can be in this ball, it rejects this part. So the new modulus becomes this. And roughly, it is just this. It is saying the soup of doing well on the P and doing well on the Q. Right? And it's a refinement, and you can show that there is also an adaptive procedure that can get this refinement. It's a more complicated adaptive procedure. I won't get too much into it. It's always better than the mean. It's always better than the rate I showed under the weak modulus. It's always at least as good. It's always upper bounded by that rate. And I'll stop there for this thing. Okay. This paper is a first version of various things we are thinking about, and we're hoping that the first version took us almost a year. The second version was supposed to take us a month. We still haven't done it. So, but the first version contains everything I've spoken about so far. In the second version, we're trying to understand much better in which exact situations is it that this second modulus is strictly better than the first one. And why is that an important question? Because the first one characterizes essentially a lot of the measures of distance that have been proposed in the literature so far. So that allows us to say that these measures of distances are of this type, right? And then they cannot solve particular problems that this one maybe is solving. So it is a step towards that direction, trying to understand a unified view of what has been done in the field. All right. Do I have a minute? How much? Yeah? 5? Okay. All right. Is this too much so far, or can I say something?
Run out of time.
All right. Okay. I'm tired, that's why. But let me talk about negative results before I get to say all that is bad about everything I just told you. I didn't run out of time, so I had to say it. So, okay, so negative results. Now, the question was for us here, how well do these ideas capture other problems that are related to domain adaptation? So far, in domain adaptation, what have we looked at? We've looked at the case of a single hypothesis class and a single source. Some related problems that we have multiple sources. Do these things capture it well? Another is we have multiple hypothesis classes. We are in a model selection setting. Do these things capture it well? And so it turns out that we have negative results in both cases, which for me, negative results are interesting. It tells us really the limits of our theory more than about what's possible in practice. Why? Because we do know that people do multi-source and multitask learning quite a bit in practice, and it does well. So that tells me that this is not fully capturing everything that's happening. So that's how I view negative results, right? In the model selection case, I don't have time to get into it, but imagine where the problem is in model selection is this. What have we seen so far? The distance between P and Q depends on the model class, right? So in model selection, all of a sudden, my trade-off is more complicated. It's no longer just a trade-off on the complexity of the class, but it's also on the transferability of the class. And then the question there is the oracle rate. Is there an adaptive procedure that can achieve them? And the answer is no, there is no adaptive procedure that can achieve the oracle rate in general. Okay. So similar question in multiple sources. I have multiple sources, PM, n big sources. Each gives me little n data points. Let's say 100 sources, 1,000 data points. And that goes a bit to Ryan's question as to, is there an optimal weighing of the sources so that I achieve well on the target? And is it possible to find that optimal weighing of the sources? And the answer, interestingly, is that no. We started actually looking at a lot of the theory on multi-source learning and asking the simple question of what is the best rate achievable? Is it a rate that combines the total sample size, or is it a rate just in terms of, and it turned out that it is often a rate in terms of a single sample size, not the combined sample size. And we're like, why is that, right? So necessarily we felt that maybe a lot of these analyses are just not tight and they're not getting, so often what is arrived at is a rate in terms of the combined sample size plus a term that is 1 over little n. Okay, so can we remove that term? That's the question. Let me just say quickly something about it. So here is the setting we looked at. We said, let's now assume a very easy setting where necessarily we should be able to do well in terms of the combined sample size. So the very easy setting is the following, is that I have n sources, its classification, they all have the same exact H star. H star 1 through H star n is exactly the same as the H star of the target. So what we then show in that setting is that, in fact, the minimax rate, an oracle that knows the distances, the roties, that knows the distances, can achieve a rate in terms of the combined sample size, can achieve a rate in terms of the combined sample size. And then the question is there an adaptive algorithm that can achieve this rate? It turns out that ERM, again, in low noise conditions, can achieve this rate. If there is a ranking, you only told me which source is closest to the target, but not the exact closeness. There is a greedy strategy that also achieves the rate. However, outside of this, no algorithm exists that I can achieve a rate better than in terms of a single sample size, which seems to say that multi-source in the unstructured regime is impossible. We don't gain. And the whole thing we had to do was, in the lower bound, randomize the possible rankings of source to target. And that was it. And that addresses a bit the alpha. Can I choose such an alpha? There is a combinatorially huge amount of such alphas, and that's why we cannot do it. All right, so I'll stop there. Quick summary. Impossibilities in multi-source and model selection. And for me, these impossibilities, these negative results, tell me that we should, to fully understand the problem of transfer learning and related problems, we need to think about more structured settings. And what do I mean by structure? Maybe causality, maybe subspace, maybe representation learning, and such things. There are tons of people in this room that have been working on such things, which I think is great. So that's it. Thank you.
Any quick questions for Samory?
Yeah.
We haven't talked us about the model shift. What could happen if there exists a model shift?
What is a model shift?
H star P doesn't mean stuff.
No, I talked about it. Yeah.
So the best thing you can do is try going forward.
I'm not sure, but I talked about it, right? It's so even this simple definition that I had, it doesn't care, right? These definitions here, these definitions here don't care whether H star P's, H star Q's are the same, right? Does that make sense? And Here is another example of what happens when H star P and H star Qs are not the same. You sort of get to this limit. The thing I didn't talk about is that strong modulus can go below this limit. Okay.
All right. Let's thank Samory again.
Thank you.